Let's see how the current flows through a metallic conductor. In a metal, the valence electrons are not attached to the individual atoms but are free to move about the body. These electrons are known as free electrons. The free electrons are random in motion, and just like the molecules of gas in a container, they act as a charge carrier in metals and speed up the randomly moving electrons depend upon the temperature. If you consider any section of the metallic wire, the rate at which the free electrons pass through it from the right to the left is same as the rate at which they pass from left to right. As a result, current through the wire is zero if the ends of the setup every point within the wire if the ends of the wire are connected to a battery. Electric field E will be set up at every point of the wire. The free electrons will now experience a force in the direction opposite to E. As a result of this force, free electrons acquire a motion in the direction of minus E. It may be noted that the force experienced by the free electron do not produce a net acceleration because the electrons keep on colliding with the atoms of the conductor. The overall effect of these collisions is to transfer the energy of accelerating electrons to the lattice, with the result that the electrons acquire an average velocity called the drift velocity in the direction of minus E. The drift velocity is of the order 10 raised to the minus meter per second, whereas the velocity of free electrons at room temperature due to the thermal motion is several hundred kilometers per second. Thus, when electric field is established in a conductor, the free electrons modify their random motion in such a way that they drift slowly in the opposite direction of the field. In other words, electrons, in addition to their violent thermal motion, acquire a constant drift velocity, due to which a net directed motion of charges takes place along the wire and a current begins to flow through it. A steady current is established in a wire when a constant potential difference is maintained across it, which generates the requisite electric field E along the wire.